Using protractors for phasors. That's a protractor. All right, let's take a look at why we would want to use a protractor. What on earth is the purpose? The purpose is so that we can get something accurate. Okay, so first things first, let's do ourselves a nice Cartesian plane. And what I'm going to do is just show you the reason why we need to have something to give us accurate values. So I want to sketch, let's see. I'm going to choose 14 volts at 10 degrees and 30 amps at 22 degrees. Now I'm going to sketch it on the Cartesian plane. I know that that's 0, this is 90, and that means that, well, I'm not good at estimating. That's probably 45, so perhaps that is 10 degrees. I'm going to do it with an open arrow. So that would be 14 volts at 10 degrees. And then I have another one over here, and that's at 22 degrees. And this one is 30 amps at 22 degrees. Now, how accurate is that? Not very accurate. And you'll also notice that I've chosen to make the 30 amp phasor shorter than the 14 volt phasor. And that's because the relative length of the two phasors does not need to correlate to their magnitude if they're of two different types of measurement. So this is volts, this is amps. And so what this brings into the discussion is not only is my angle suspect, but also the lengths. How can I accurately represent the lengths of my two phasors if we have two very different values? And what this brings in is scale. Sometimes we're going to have very high voltages and very low currents. And if I were to sketch them at the same scale, my voltage phasor would be way off the page and my current phasor would be this tiny little dot in the middle. And so we need to sketch them at different scales at times. What is a scale? Well, a scale is something that we use to accurately portray the length of the phasor, and we use a ruler. And typically it's in a distance or length measurement per unit of measurement that we have used for the circuit, so volt or amp. It can be in either metric, centimeters, millimeters, or even imperial, it doesn't matter. The angle accuracy will be provided with the protractor. So let's do this again and sketch our two phasors, but this time let's do it a little bit more accurately. And in doing it more accurate, hopefully we get something that represents the circuit a little better. So here is my Cartesian plane again. I'm going to try to get it as bang on 90 degrees as I can. There we go, good enough for me. So what we're going to do now, I said that we had two separate phasors. One of them was 14 volts at 10 degrees, and the other one was 30 amps at 22 degrees. So 14 volts at 10 degrees and 30 amps at 22 degrees. All right, so what we need is something called a scale. A scale, how long we're going to draw each of these phasors. And so because I have voltage and I have current, I'm going to have two separate scales. These ones are going to be two different values. For the voltage, I'm going to use imperial, and I'm going to say 0.5 inches per volt. And for the current value, I'm going to say 0.25 inches per amp. And so the way that scales work is quite simple. All we need to do is take the value here, the total value of the measured value, 14 volts, and multiply it by 0.5. So 14 times 0.5. And that equals 7 what? 7 inches. The other one we have is 30 amps, and all we're going to do with that is we're going to multiply 30 times 0.25, which would be, well, 30 times 0.25 equals 7.5 what? Inches. So let's sketch these. The first thing I need is my protractor. So I'm going to first put a little dot where 10 degrees is on my page. And it's going to be as accurate as I can possibly get it. And I know it's not perfect, but a protractor sure makes heaps difference. So 10 degrees for me is right here. And I'm also going to list the 22 degrees. I'm going to sketch that right there. So I got 10 degrees and 22 degrees. Now I take my ruler, and because it's imperial, I chose imperial because the numbers are huge on my ruler here. You can actually see them. So what we're going to do, I'll move it over. There we go. 7 inches was at 10 degrees, right? 7 inches was at 10 degrees. So here is my 10-degree mark. 7 inches is right there. And this was a voltage. And so because of that, open arrow. What about the other one? That was 7.5 inches, and that was amps. So let's put it back on, line it up with my angle. 7.5 is right here. There we go. And so what we get is 2 values that are accurately portrayed in their visual representation. So this one being 14 volts at 10 degrees, and this one being 30 amps at 22 degrees. So it's an accurate method of displaying information. But wait, there's more. Yes, yes, just when you thought it was over, there is yet more excitement that we can do when it comes to accurate phasors. Let's sketch another one. Okay, so this time what I'm going to do, I'm going to use metric. There we go. And here's my horizontal. I'm going to use metric, and what I want to sketch is 100 volts at 70 degrees and 50 volts at 20 degrees. And because these are both the same form of measurement, as in volts, I can use the same scale for both. I have to use the same scale. And so what I'm going to use is 0.1 centimeters per volt. So that means that this one up here will be 10 centimeters in length, and this one will be 5 centimeters in length. So let's put our protractor onto the page again. I'm going to choose 10 degrees and 70 degrees. So here's 10 degrees, here's 70 degrees. And now with my ruler, this time I'm using metric, so you can't really see the numbers. You're more going to have to trust me, but believe me, it works. Okay, so for the 20 degree, whoops, 20 degree, not 10 degree. There we go. Let's do 20 degrees, shall we? Excellent. There we go. Excellent. So 20 degrees, and I'm going to do 50 volts, which would be 5 centimeters. Okay. There we go. And it actually ends up being right here. Okay. All right. So this is 50 volts at 20 degrees. The other one was this one. It's going to be 10 centimeters in length. It's going to start here. It's at 70 degrees. And this is 100 volts at 70 degrees. Now remember, we can add phasors together, right? We can add phasors together. And if I were to add phasors together, I have a few different options. What if I wanted to know the total sum of these 2 phasors? Well, I know we could do an HV table. That makes sense. Those are pretty slick, not too long, and you get an accurate value every time. You could use mode 3 if you have the right calculator and you're comfortable with using that different mode function. The last method we can use if we have accurately sketched phasors is something called a tip-to-tail method. So I'm going to say tip/tail. The tip-to-tail method means that we take one of these phasors, and it doesn't matter which one. I could take this one and place it so that the tail of the short phasor is at the tip of the long phasor. So we could take, look, through the magic of computers. Oh, there we go. See, I can move it up here. At the end of this phasor here, that tip, that would be the end of the new phasor, which is the total. So what we do is we take one of these phasors and we move it up there. And so you could, if you wanted to, just put your protractor up there and sketch the new line. But essentially what we're doing is we're drawing a new line all the way back down here. So let's do mode 3 on our calculator and just work out what it should be. Let's see what it should be. So I'm going to take 100 volts at 70 degrees, and I'm going to add to it 50 volts at 20 degrees. It tells me in my calculator that I should have 137.5 volts at, well, we got to do EXP, 53.8 degrees. And so what is this value? This is E total, or simply the sum of our two phasors, right? E total, or the sum of our two phasors. So let's see how close we get. 137.5, how long should that be? That should be about 13.7 centimeters. So I'm going to put my ruler here, 13.7. So you can see here, oh, there we go. 13.7, great. And it's kind of hard to line it up with this little movable item here, but it should be right there. 13.7, looks good. Put a little dot. And then we can draw a full straight line all the way to the end there. And what this represents is the new source, or the total of these two phasors. This is 137.5 volts at 53.8 degrees. But wait, we didn't actually measure the angle, did we? You're just trusting me. Okay, I'll put the protractor on here and take a look. Look at that. 53.8. And again, I understand that you probably can't see this phasor accurately, or rather the protractor, but we kind of all agree that there are equal divisions of degrees and angles along here, and when you get your own, you can easily accomplish this task. Okay, so last item that I'm going to do here is just show you how we can utilize using scales and the protractor when we have phasor values that aren't as even as what we just saw there. Even values, typically people don't have an issue with, but when values are not even, for some reason we find those a little bit more confusing. So this one, I'm going to draw, let's see, 126 volts at 47 degrees, and I'm going to draw a current value of 30 amps at, oh, let's say, I don't know, 25 degrees. There we go. Now I need a scale for each of them. So scale for voltage, scale for current. The scale I'm going to use for my voltage, or that's given to me, let's say it's given to me, is 0.083 centimeters per volt. And the current is going to be 5.687 centimeters per amp. Oh, that seems like it's going to be really complicated. Well, actually, it isn't. It's actually quite simple. So all we're going to do is take our value and multiply it by the scale. 126 times 0.083. 10.45 centimeters. 30 times 5.687. Whoops, should be 3. There we go. 3 times 5.687 equals, oh, looks like we've got 15. There we go. Sorry, I got lost in my own thoughts there. There we go. So 3 amps, should have a decimal there, times 20, or times 5.687. So 3 times 5.687 gives me 17 centimeters. Awesome. Okay, so off we go. Let's complete it. It's going to give me something very accurate. And again, all we're doing is we're taking our value, amperage, multiplying it by the scale. So first one, 25 degrees. 25 is right here, and 47 is right there. There we go. My 25 degree is 17 centimeters, which means it is all the way out there. This is my current phasor, and this is 3 amps at 25 degrees. And then the second one is 10.45. So 10.45, let's see, 10.45, there we go. That is my voltage phasor, and that is 126 volts at 47 degrees. So, protractors, useful, and rulers, useful. The reason that we show you these two things is so that you can draw accurate phasors. Accurate phasors help to solidify the concept of the calculations that we are doing and the relationships of the electrical properties. You need to understand how these things correlate together, and because of that, a protractor and a ruler are extremely helpful. So there are a number of examples that we will do throughout the course that will ask you to sketch the phasor accurately, and they'll give you scales. I encourage you to do each of those as shown here in our little tutorial.